Hello and welcome. Today we're going to delve into the actual content of the lecture series, and we're going to begin with talking about some definitions of circuits and international system of units. And we're going to talk about electric charge, electric current, and some quiz problems to test your understanding of what was talked about here. Now, if you've taken any physics or circuit theory classes before, either in college or in high school, then you might get bored a little bit, but just to cover our bases and make sure everybody's on board, I do have to start with these fundamental topics, so just bear with me for a couple of minutes. So let's dive right into it. So what do we mean by electrical circuits or circuit analysis? So to apply our circuit analysis techniques, we're going to be working with electrical circuits, which consist of the interconnection between a series of electrical elements. So for example, here's a generic circuit without any values or explicit components. So there's some generic components. They could be resistors, inductors, capacitors, or any other components. In this case, they're interconnected in some manner, and we have a voltage source here. It could also be a current source, but in this case I've chosen voltage source. And another symbol for voltage sources are what you see here, which is a very old symbol as far as I've seen. The one I like to use is this one. It's just my preference, but they're interchangeable. So the next concept is the international system of units. And now, what do we do as engineers? Is we like to measure quantities to be able to communicate about them with each other and present our results. So what this is it is a standard language for measuring physical quantities. So whether that is for electrical experiments or any other astrophysical or any other scientific experiments, we're going to be using these units to uniformly and effectively communicate results of experiments and basically theoretical measurements or theoretical values that we should be finding. Now, they're composed of 7 primary units, of which every other units are derived from, and I'll show you what I mean by that in a minute. Now, the nice property about these units is that they're expressed in terms of powers of 10. So what that does is very nicely you can create, what they've done is they've created prefixes so that they would correspond to powers of 10. So for example, if you have 3 seconds, a quantity which is 3 seconds, you can also represent that using milliseconds, which would be 3,000 milliseconds. And then just real quick, you might already know this, but the way I like to think about that is, so 3,000 milli is 10 to the minus 3, so 10 to the minus 3, these are being multiplied, so 10 to the minus 3 is the same as 1 over 1,000. So what's going on is you're multiplying 3,000 by 1 over 1,000, so that's 3. And let me not forget the seconds here. So milliseconds is equal to 3 seconds, which is the same thing as what's here. You could also say that's 3 million microseconds, because micro, which is represented this way, is 10 to the minus 6, or 1 over 1 million. So when you multiply those out, those zeros cancel and you get 3 seconds. So that's a quick example of how that is useful in terms of representing these quantities. Then the next idea here is the 7 units that we discussed, the 7 fundamental units, which are for mass, which is measured in kilograms, and the symbol is kg. You have to be mindful of the capitalization also, because some symbols are used for some quantity and others are used for others. The capitalization of them is used for something else. So length here is measured in meters, and that's represented with a lowercase m. Temperature is in Kelvin, and that's uppercase K. Time is in seconds, and that's lowercase s. Luminous intensity, which is for measuring light and such phenomena, is candela, and that's CD, lowercase. Charge, electric charge, is a coulomb, measured in coulombs, and the symbol is uppercase C. And another similar quantity which is related to charge and is derived from it is electrical current, which is measured in amperes, and the symbol is uppercase A. So now that we've seen the prefixes, let's look at I'm sorry, now that we've seen the measurements and their corresponding units, let's look at the prefixes. So it looks like the screen is lagging, so bear with me for a minute. Let's see. I have to drag it up here. So now for electrical engineering, unless you're working with power circuits, you're not really going to need any of these positive powers of 10. Probably not very likely, or maybe up to kilo. But really, I'm going to start it down here. So if you have 10 to the minus 15, that's represented by femto. 10 to the minus 12 pico, and so on and so forth. Really what you'll see most likely, if you're just doing typical circuit analysis, not high power or anything like that, you'll see, I hardly ever see centi for this application for circuits, although you can see centimeters, but that's not, that's for length, not for electronics. Or deci, that's probably seldom used also. Deca, I haven't really seen it much, used much. So really milli, micro, nano, maybe if you're working with very sensitive or sensitive measurement equipment that measure picoamps, or if you're working with capacitors that are very small, you could see picofarads or femtofarads. So that's the concept there, and you can see all the corresponding symbols and prefixes. So now just a quick example. So for example, if you have, as we saw milli, let's do nano now. So if you have nano amperes, that would be, so if you have nano amperes, that would be 10 to the minus 9 amperes. So the way that's useful is you don't have to keep expressing things in terms of powers of 10. You can just write, for example, 10 nanoamperes instead of having to write 10 times 10 to the minus 9 amperes. That's the one of the usefulness, one of the uses of that. So let's go to the next concept, electric charge, which is very fundamental to this subject. So it is the basis for all electrical phenomena. A charge is an electrical property of atoms. So if you have, if you remember from basic physics, if you have a very simplistic model of an atom, you have, for example, hydrogen. You have a ion here, or a nucleus of the atom, composed of a proton. The way we represent the field, the electric field that is produced by charges, is by showing arrows that represent the vector field for the electric field. Now, for the positive charge, it's going to start, the convention is that it's going to start from the charge and move outwards. Now, for the electrons, they're going to be starting from the outside and moving inwards. And what that does is it basically shows that positives and negatives attract each other, and positives and like charges repel each other. Now, let's go on to the fundamental charge of electrons and protons, which is a topic of physics, and something very interesting about it that I'm not going to get into too in depth here because it's not relevant for us, is that all electrons and protons have the same fundamental unit of charge. So the elementary charge is 1.602 times 10 to the minus 19 coulombs. But the interesting thing here is that electrons and protons, although they have the same charge, they don't have the same mass. So that leads to very interesting consequences that you can study in physics. But very quickly I can tell you that, well, if you apply an electric field from, say, A to B, if you have electrons passing through, due to their mass, they're going to feel a different acceleration than protons would. And there are some applications for that in the physics world and in experimental setups. But we will not get into that here because it's not relevant for us. It's just an interesting fact to consider. Now, here's a question. So how many electrons or protons would be in a 1 coulomb of charge? So let's see. If you have 1.602 times 10 to the minus 19 coulombs for every charge, then if you have one giant blob of a coulomb, assuming that it can even stay there, because realistically it won't, because it's going to fly apart since like charges repel. What you can do is think of it as, okay, the way I like to think about it is, okay, here's one blob of charge, 1 coulomb of charge. Now, if I break this down into each individual charge of for an elementary particle, elementary charge, you're going to have 1 coulomb divided by 1.602 times 10 to the minus 19 particles per coulomb. So what's going to happen there is, let's see, that's going to give you 6.24 times 10 to the 18 elementary charges in a given coulomb. That's a huge number, and it makes sense that 1 coulomb would be composed of that many particles or elementary charges. Now let's talk about the law of conservation of charge, which states that charges cannot be created nor destroyed, which is very important because of that fact you can have a circuit. You can have a circuit that you can have currents flowing through it and it doesn't just die away. It continuously works because charges cannot be created or destroyed. Although that's one observation of it, there's more fundamental observations, which is that you and I can be here and we can exist, and our hand doesn't just disappear because the charges that make it up have to obey this rule basically, and every other charge, every other particle in the universe obeys these rules. So that's an interesting observation there. Let's go to the next concept here, which is I don't want to say polarity, I want to say the direction of current. So suppose you have a piece of wire that I've magnified here, and I've showed some representative charges here. So you have ions, you have the lattice structure of the metal, say copper for example. Now what's going to happen here is that you have the mobile charge carriers, which are the electrons, and you have the ions, which are just bound and they cannot move. So when you apply an electric field, or in other words a voltage, which is really an effect given due to electric fields, what's going to happen is that so if you have a polarity given as such, so plus and minus in this direction, the electric field points from the positive to the negative. So the potential at this point is higher than this point, and what's going to happen here is the same polarity is going to be applied here, the same field, and that electric field is going to attract, if you remember from physics, it's going to attract negative charges this way but push positive charges in the other direction to the left here. Now the ions are not able to move because they're bound in a lattice in a metal. So what's going to happen is that the mobile charge carriers in the valence band are going to be excited by the field. They're going to be responding to the field that is applied here, and they're going to be moving in this direction. Now the conventional current is defined as the flow of positive charges from one point to another. So in this case, the conventional current would be going in the same direction as the electric field. It would be going this way. But we know in reality, we have to keep in mind that really the positive charges are not the ones moving in this case. The electrons are moving in the opposite direction. Now, to make sense of this better or more, we can think of what's going on here in this demonstration. If you have a couple of charges here in this region, and they're charge neutral in a charge neutral region, and if you move 4 positive charges, what's going to happen? You're going to have what's going to remain is, assuming that it can do so, assuming that it's not going to fly apart from each other because they're locked charges, you're going to have 4 electrons here, and you're going to have 4 positive charges here. Now let's keep this effect in mind. So now you have negative 4q here and positive 4q here. Now let's look at what's going to happen if you have electrons moving in the opposite direction. So this vector that represents current is going to be the negated version of this vector. So you're going to have a negative 4q. If you remember vector algebra. So if you multiply this vector by negative 1, you're going to get the opposite of it, which is this vector over here. So now let's look at the minus negative charges, and let's see what they're going to do. So if you move these charges to in this direction to the left, you're going to have minus, 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 and plus, 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 plus. Now, if you observe here, the same effect is going on if you move 4 positive charges from left to right here, or 4 negative charges from right to left. We can see that that's the same effect. But to avoid these negative signs, people typically stick with the convention of the conventional current flow, which I described here. Now, to make even better sense of what's going on here, I like to think of this as heat. So if you define So even though coldness doesn't really exist, even though heat is just excitation of molecules, random thermal motion of molecules that heat things up, what's going to happen is if you imagine a cabin in the woods and it's a cold winter night, you're heating up the cabin, and inside of it you have some, let's just call the positives as heat. So there's a higher temperature here than there is on the outside. Now if you open the door, if you define the entity of the cold as one entity and the hot as one other entity, you could say, effectively you could say, to do the algebra on it, you could say, for example, 2 units of heat have moved outside if you open the door. You could also say that, in the same breath, you could say that 2 units of cold have moved inside. But if you think about that, that's the same effect. And that's sort of vaguely analogous to what's going on here with the current. The end effect is the same. So now let's go on to the next idea, which is electric current, which is related to electric charge. So electric current is defined as the change in charge per unit time. Now, a visual image of this would be if you have a certain amount of charge passing through a certain volume, and that's going to happen in a given time, delta t, and that is my delta q. What's passing through this cross section is defined as the current. So if you remember your calculus 1, differential calculus, the limit is the change in time approaches 0, delta t approaches 0 of this quantity is going to give you the instantaneous current. And similarly, the total charge in a given region is going to be given by the integral of the current from one time to another. Now, the next concept here is DC versus AC. So direct current versus alternating current. So direct current is going to be conventionally represented by a uppercase I, and AC current, AC is going to be represented by a lowercase I. So direct current is just you apply a DC voltage, you're going to apply a constant voltage across a resistor, you're going to get a constant current, at least ideally. Now for the alternating currents, you're going to be applying a alternating voltage across a certain load, and you can have this alternating current. Okay, now let's move on to the quiz. So let me just real quick show you the questions. I would like you to stop the video and try to test your understanding of what was talked about here, although it was brief. I'll also solve them once you give it a try. So here's number 1. How much charge do 10,000 electrons carry? Question 2 is the total charge entering a device is given by a Q of T, which is 3T times sine of 6 pi T microcoulombs. Find the alternating current at T equals 2 seconds. The last question is, given that the current flowing through a device is this piecewise function defining the current at these times, find the charge entering the device between T equals 0 to T equals 3. So please give it a go, and I will solve starting from problem 1. Alright, I'm assuming that you've given it a try. Now let's go to problem 1. How much charge do 10,000 electrons carry? So as you remember, 1 electron carries 1.602 times 10 to the minus 19 coulombs. Now this many electrons is a matter of, for finding them, the charge that they carry, that is a matter of using dimensional analysis and just a conceptual understanding of what is going on. So we have this many coulombs per electron, and you're going to multiply that by the number of electrons. That is electrons will cancel, and you're going to have this many coulombs for the 10,000. So if you have 10,000, you're going to add 4 here to the exponent. So you're going to have 1.602 times 10 to the minus 15 coulomb total for the 10,000 electrons. So that is my answer here. Now the next question is the total charge entering a device is given by this function. So now this is a periodic trigonometric function, so that's how we know that it's going to be an AC current that we're going to be dealing with. So if you remember the definition, the current, the alternating current is given by the derivative of charge. So now what we're going to have is the derivative of 3t times sine 6 pi t, and that is all in microcoulombs. Now we have to remember that that is for t equals 2 seconds, but I will plug that in at the end, which is typically what you want to do when you perform these operations. So let's see, this is a we're gonna have to use product rule here. So let's first take the derivative of this guy. And then why I know that, by the way, is if you remember from calculus, is that you have a function of t and another function of t multiplied together, and the derivative is with respect to time. So we have to take apply the product rule. So first let me take the derivative of this guy. That's going to give me 3. I'm going to multiply by the same guys here. So sine 6 pi t. Now add to that this guy 3t times the derivative of this guy now. So cosine 6 pi t times the derivative, now the chain rule, derivative of the inside is 6 pi, and that is all in microcoulombs. Now let's simplify even further, and we're going to get, let's see, I could factor out with 3, let's see, yeah, that should be good. So 3 sine 6 pi t plus let's see, 6 pi t cosine of 6 pi t, that is all again in microcoulombs. Now the next question is, let's see, given that the current flowing through a device is this current, this function, find the total charge entering between time 0 to 3 seconds. So now let's first, I like to graph these sorts of problems so that I have an idea of what is going on physically. So what you have is, you have some device, let's first represent it. Some voltage was applied to it and some charge, some current is going through it. And let's just show it this way, I. Now the graph for that would be, all my curves are coming out bad, all my graphs. Let's make it better. Now it's going to be 2, a constant value 2 from 0 to 2 seconds, that's time in seconds, and that is current in amperes. Now from t onwards it's going to be 2 times t squared. So now it's going to look like, if you have t squared, that's going to look like that. If you have 2t squared, that's going to be even steeper. Now it's going to look like that. Now it's saying from t equals 0 to 3 is where you're interested in. So you want to find the area under the curve for this region. That is going to give you the charge, total charge that has been accumulated in the system, or passing through the system, because it may not have accumulated, it must have flown out. So let's see, that's going to be the total charge is going to be the integral, let me just say q, because I don't want to say as a function of time because it's just a constant value. So q is equal to the integral from t equals 0 to 3 of let's see, I don't want to do that, I want to break this down already. Let me just do it generally first. I of t dt, which is given from t equals 0. We can break it down, the integral down further to the piecewise function. So now we have 2 dt plus integral from t equals 2 to 3 of 2t squared dt. Now solving this problem, then we simplifying it, we're going to get 2 times t evaluated from, I did that sort of badly, 0 to 2 plus, let's see, 2t cubed over 3 integral, or in the balance from t equals 2 to 3. Now let's see, what's the final answer? You're going to have 2 times 2, because the 0 is going to not matter, so 2 times, let me just write it just in case people don't remember their calculus. That's going to be that answer. Then you're going to add 2/3 times t cubed, so 3 cubed minus, let's see, 2 cubed. Now what is that going to give me? That's going to be 4 plus 2/3. 3 cubed should be 27 minus 8, which is going to be what, 19? Did I do that right? 3 times 3, 9, 27. Right, so then 8, subtract that, that's 19. Then you're going to get a sort of an odd number, so 4 plus 2/3 times 19. That is going to be what, coulombs? If you plug that into a calculator, you should be able to see what that is. But let's see, if it was 21, you would have gotten 7 to 14. You would have gotten about 18, but you're going to get slightly less than that here. It's going to be roughly somewhere between 17 to 18 coulombs. Anyways, I'm probably out of time here, so I'm going to see you in the next video. If you have any questions, please leave it in the comments, and I'll either make a follow-up video or just answer to your question there. Thank you.